So this video is on reducible chain. So we already discussed what are the different states of a reducible chain. So now it is a reducible chain. So let pi be a distribution on that script S, the state space, and C be a subset of that script S. Now we say that pi, the distribution pi, is concentrated. It concentrated on that some set, that set C concentrated on C if it is obviously that the definition is clear from the term concentrate on C, that is pi x equal to 0 for all x not belongs to C. So outside C, every element has that initial that distribution is 0, and that probability is 0. So this is concentrate on C. That is called the distribution concentrate on C. Now theorem. Let C be an irreducible closed set of positive recurrent state. Is a set of all positive recurrent state. Then the Markov chain has a unique stationary distribution pi concentrated on C. So there is a unique stationary distribution which is constant on C. So if there are several irreducible closed sets, C1, C2, C10, so then it is not unique on if it is on C1, there is a different stationary distribution may be on C2. Obviously, if it is a concentrated on C1 and a distribution concentrated on C2, that must be obviously different. So C1, C2, Cn are say distinct irreducible that component, that irreducible set of that state space. Then there is a unique distribution, stationary distribution concentrated on C1. There is a unique distribution which is concentrated on C2, but that distribution on C1 and that distribution on C2 is not obviously not same because the set is different. So that's the idea. So if there are 10 many irreducible closed set, then there are of positive recurrent, there are 10 different stationary distribution is there. We don't know whether there are more than that or not. Actually, mixture of these two also a distribution. Mixture of all this. So the whole distribution on C1, the distribution on C2, you can just mixture of these two. Lambda of distribution pi 1 plus 1 minus lambda of pi 2. So it is a mixture of distribution also will be a stationary distribution. So actually there is infinitely many distributions. So the distribution, and that distribution is given by pi x, that we already done in the previous lecture, that 1 by mx for x belongs to C, and obviously 0 is not belongs to C. So this proof left as exercise. This is just a consequent of the previous lecture. We prove it for if the Markov chain itself is a positive recurrent in the Markov chain. All states are positive recurrent. That means it is irreducible over that. Sorry, is an irreducible Markov chain, and is one state is positive recurrent, the every state is positive recurrent. It may so happen that a Markov chain is all states are positive recurrent, but still is not irreducible. Every state is absorbing state. So if every state is absorbing state, that means it is a positive recurrent Markov chain, that and every singleton set is reducible, and any doubleton more than one element is not reducible. So this proof is just coming from the previous lecture, that what we have done for the irreducible Markov chain with positive recurrent state. So, and obviously, if you know that if the two distribution, then the mixture is again a distribution. So let now the one consequence is this. So let pi 0 and pi 1 and this be distinct stationary distribution. For a Markov chain, then obviously what happens? Then for any 0 less than or equal to less than equal to 1, that pi alpha, the mixture of these two distribution, 1 minus alpha pi 0 plus alpha into pi 1, this also a stationary distribution, is a stationary distribution. Basically, it's a distribution, and as well as it is stationary also. So you have to first check whether it is a distribution or not, and then you have to check it is stationary distribution. And obviously for and the another result is true, is this number 2 is for alpha beta, which is between 0 and 1, and alpha not equal to beta, then that pi alpha is not equal to pi beta. If you take two different alpha, then that stationary distribution is different. So that means that the infinitely many stationary distribution if there are two stationary distribution. So basically it's from a vector space. All the stationary distribution forms a vector space. Basically any linear combination of that is again in the stationary set of stationary distribution. So that means stationary distribution forms a vector space. Oh no, not that. There is a problem. No, it not form a vector space because this alpha is cannot be greater than 1, right? So it is not form a vector space. It actually forms a convex set. And this forms a convex. No, sorry, it's not a vector space because its alpha cannot be greater than 1. So it's not a vector space. It is a convex set. You know what is called convex set. So if two points are in the set, then they're convex combination. This is called the convex combination. These are not the linear combination. So every convex combination belongs to that set is called the convex set. So that's it is a convex set. So the different results are also trivial from here. That let script SP denotes a set of positive recurrent state. So denotes the set of all positive recurrent state. Positive recurrent states of a Markov chain. Then what happens? Then their different results are true. The result number 1, if that set is empty, then the chain has no stationary distribution. That we've already proved in the previous lecture. There is no stationary distribution. So stationary distribution always concentrated on the state of positive recurrent state. If this is non-empty and irreducible, then there is a unique stationary distribution already proved in the previous class. Then chain has a unique stationary distribution. And obviously the last one is this is non-empty and this is not irreducible. It is a reducible chain. Then it is clear. Now if is non-empty and reducible, not irreducible, it is a reducible set. The chain has infinitely many infinite number of distinct, that we actually proved in the previous result. So for any alpha beta, different alpha beta where distinct pi alpha and pi beta, and both are stationary distribution and the distinct, and you can just run alpha and beta through the 0 to 1. 0 to 1 is just infinitely many number. So your infinitely many distribution, infinitely many number of stationary distribution. So if this is a reducible set, then you can have two different reducible set of positive recurrent. Then this has infinite number of so that is a script SP. So set of all positive recurrent state is non-empty as well as irreducible. Irreducible means there is a more than one irreducible component, and then the say pi 1 for another one, pi 2 for another, say pi 3 for another. So we just take the mixture of this all the convex combination of this. So this is interesting and very important concept on reducible chain. Now convergence of this all this thing, convergence thing. So now convergent, the question of convergent of different stationary distribution. So is a steady state or not? Is there any state start from any distribution, whether it is converge or to the stationary distribution or not? If you start from the stationary distribution, is always in that distribution. But if you start from the other distribution, whether it is steady state or not, so whether the limit is actually converged to the stationary distribution, some stationary distribution or not, that's the question. So now the question of convergence to the stationary distribution, to some stationary distribution actually. So if there's a two different irreducible state set with positive recurrent, now if some distribution concentrated on C1, that cannot be converged to the stationary distribution which is concentrated on C2. That can be true. So that's then whether the question is whether it's concentrated on C1, the starting distribution, initial distribution, whether it's a converts to a stationary distribution which is concentrated on C1. That's the question. So now what we see that we have seen that if that's Markov chain, that Markov chain is an irreducible positive recurrent. So this is an irreducible positively recurrent Markov chain. That means every state is positively recurrent and it is also irreducible. So then it is a unique stationary distribution. So positive recurrent Markov chain having, so pi is its stationary distribution, say pi as its stationary distribution. So actually we are dealing with the irreducible component only. That is the important. So with the two irreducible component, then we know how to mixture. So we just consider we just discuss the case whether just single irreducible thing. So that whole Markov chain is irreducible. So stationary distribution. Then what we say that then for any xy in the state space at a limit n tends to infinity, 1 by n, that sum over m equal to so m equal to 1 to n, that Pm xy is equal to limit n tends to infinity gn xy n, which is equal to pi y. So that we see, we already seen in the previous lecture. Now we'll see that we want to see when the stronger result, that this summation is goes to pi, but this is not the limiting thing. This is sum over then. So they take the sum, then so that's C0 mean. So C0 mean converts to the something. So the stronger result is whether the sequence converts to that. So if C0 mean the sequence converts to L, then C0 mean converts to L. C0 mean. But if C0 mean converts to N, the sequence may not converge to N. So if A1 plus A2 plus AN, see if AN tends to L, then A1 plus A2 plus AN divided by N tends to L. That's true. It's called C0 mean. But if A1 plus A2 plus AN by N, that tends to L, it's not true that AN tends to L, that or may not be converged actually. May not converge. Oh. Something like say 1 minus 1, 1 minus 1, that sequence doesn't converge. But if I take say 1 plus minus 1 plus 1 up to n times, divide by n, that actually converges to 0. Because the sum is either 1 or 0, so divide by n, that is actually comes to 0. So that means C0 mean goes to 0, but this sequence doesn't converge. But the other way is always true. The sequence converges to L, then C0 mean that the sequence of C0 mean converges to the L. Now that's the question. If the C0 mean converges to the that, so whether is that result is true, whether the stronger result actually, the stronger result, that what is the stronger result? The stronger result is limit n tends to infinity, that Pn x y, this is whether tends to pi y or not. That's the question. If this is true, then we can say stationary that distribution that goes to that Pn x y, that goes to the stationary distribution, converges to the stationary distribution. So, whether this result is hold or not, holds or holds, whether it is hold, and if it is not hold, if it the what happens if it is not hold? If what happens when it is not hold or fail to hold? If it's hold, then it is okay. There is a stationary distribution, steady state stationary distribution. But if it's fail to hold, then what happens? That we have to see. Now to see this, we first take x, let x belongs to S, such that Pn from x to x is positive for some n. That means start from x and goes to coming return to the x for some n, and for some n, some time, that probability is positive. Now that is what? That is rho xx, which is that p start from x, the heating time at x is finite. That is positive. So that is positive. So we assume that such a x, that this rho xx is positive. Now we define a new term that is called define its period. Its period, the period of x, its period dx. That is period is called dx. What is the period? Is that by the GCD of all such bar for which it is positive. So we know there is for some n it is positive. Now we want to show the for which value of x is positive, and then we are checking what is the, we are taking the GCD of all these things. So it may be so happen, say, so for even number of time, after even number of state, that 0 visit to the zeros, like a random walk. So it can't be start from x, you can't return to the x. It is a simple random walk. It can't return to the x after an odd number of times. So if n is odd, we can't return. So now this period is 2. That means from 0 you can go to 1, then come back to the 0. By 4th step you can go to the 0. You can by 6th step you can come back to the 0. So for any even number you can come back to the 0. So GCD is 2. So that is the period is 2. But if say the absorbing set, that the period is actually 1, that right, the GCD is 1, so period is 1. So that's the important question, that whether its period is 1 or not. Now, what is the period? That period is obviously that greater than equal to 1, and that must be less than equal to the minimum of all this set. So for which that greater than equal to minimum of such n, such that sorry, that minimum of all natural number and natural that Pn that x y positive, that minimum number you can't be the DCD cannot be greater than the minimum number. So that is result. It's just a trivial thing. So now the theorem is this important theorem for towards the end, that if x and y are two state, whether it is recurrent or positive recurrent does not important, each of which, it is a simple Markov chain property, if of which leads to another. So x is to y, so associate x and y is associate, x leads to other, then it is you can always guess that then the dx must be equal to dy, the period are equal. So if one leads to another, so x leads to y, y leads to associate, then dx equal to dy. It's not true if x leads to y. Maybe y is absorbing set and x is not absorbing set. And maybe that if it do not come back to, then we say that period is infinite. So it may swap in the period is infinite. Maybe period does not exist. Maybe period is set 5 or whatever, but the period of the absorbing set is 1. So x leads to the y. Y is the absorbing set. So then it is not true. But x leads to y, y leads to x. The idea is this, that to period is same. Proof is slightly just calculative. It needs some calculation. So let n1 and n2 are two natural number such that, so you take the n1 step transition from x to y is positive, and n2 step transition probability from x to y is also positive. Sorry, that should be y to x. Y to x. Now, since x leads to y and y leads to x, so this such a n1 n2 are exist. Such two natural number exist. Now, from n1 step, it is positive probability x goes to y, and from y to x, it's come back to the x for n1 step. So it is that implies you can just guess that this is n1 plus n2 step, x come back to the x is positive with the positive probability. That's the product of these two. Maybe any other way to come back. So it is that probability is actually greater than or equal to the product of these two above two. Now, what this tells us? This tells us actually dx that divides n1 plus n2. So GCD divides any number which is in the set. Now, if say Pn xy is positive, then what happens? So for any n, if it's Pn xy is positive, other than n1 also, n1 is such a n, but there be other n, then what happens? Then P n1 plus n plus n2 x from x, that is positive. It is start from x to y, then no, that should be y, that should be y. Sorry, it is not x, it's y. It's y. So start from x, goes to y with n1 step, then go to y is n2 step, n step, then y to x is the n1 n2 step. So this is true, and that implies dx divides n1 plus n plus n2. And what this mean? That divides d divides this. So that's actually 1, and from 1 and 2 we conclude that dx divides n for any n for which Pn yy is positive. Now, what is the meaning of that? What is the meaning of that? Dn divides n. That means dx is a divisor. Dx is a divisor of all number, all such n, all numbers, all integers, all natural numbers in the set. What is the set? The set contain that x greater n such that n greater than equal to 1, that set of all natural numbers, and the probability from y to y is positive. So d is what is the meaning of that? So this is a common divisor of that, means dx is divides dy, or dx less than or equal to dy, because dy is a GCD and dx is the common divisor of that set. And we can just do the similar way. It is just from x to y. A similar way, similarly, a similar argument we can show that dy divides dx. Hence, dx equal to dy. This completes the proof. This is very interesting. So what we actually prove? We prove that this result, that the states in an irreducible Markov chain. It may not be positively recurrent, whatever it may be, null recurrent or transient, whatever. In an irreducible Markov chain, it may be transient because it may be infinite set Markov chain. If it is finite, then it is obviously a positively recurrent state. All states are positive. But it's infinite, maybe transient state. All the states are transient. But if it is irreducible, that means every x goes to y and y goes to x also. Irreducible Markov chain have common period. So that is the important property of the irreducible set, irreducible component of the Markov chain. So every irreducible component has a common period. So two different Markov irreducible component may have two different common periods. So that means a period of the something is not not only the property of the single element, single state. It is a property of the whole irreducible component. So we can talk about the period of the irreducible component, not only the particular element of the set. It's actually period of that component, period of that component. So if there are 10 reducible components, then we say that d1, d2, d10 are the 10 period of corresponding period of the 10 irreducible components. So that is the important thing. So common period D. So we say now we say that a chain is periodic. We say that chain is periodic. That all the chain is periodic with period D if that D is positive. That D is positive. With period D, that D is positive. Sorry, D is greater than 1. And D always D is greater than or equal to 1. GCD cannot be less than 1. So it is always greater than or equal to 1. And if we say it is aperiodic, and aperiodic, so it is not periodic actually, or call aperiodic if D is equal to 1. So D is always 1. D is always greater than or equal to 1. So whether the question is periodic chain or not, like a simple random walk is not periodic. It is a periodic period 2. Simple random walk. The question is aperiodic or not. Its idea is clear that if it is not aperiodic, if it is a periodic, then there is a problem. Then that distribution cannot lead to a stationary distribution, because it's for every odd it is 0, and for even if it is a converge, then that limit should be goes to 0. So that Markov chain must be aperiodic. Otherwise, this is the idea. Otherwise, it cannot be had this limit goes to a stationary distribution. For example, that queuing chain is aperiodic. That example is there, and the queuing chain is aperiodic. The queuing chain is aperiodic. And Barth jet chain is also aperiodic. Barth and if Rx is 0, then Barth and jet chain is period 2. Then it is just a random walk. Barth and jet chain is aperiodic. if that Rx is positive, that Rx does not increase or decrease, no death, no birth, that is positive, then by one step you can go with positive probability, you can come x to x, return x. And obviously, if Rx is 0, then period is what? Then period is clearly that period is a, like a random walk, period is just 2. Now the next theorem is a very important theorem, and towards the end, we are actually coming to the end, and this theorem is the last theorem for the discussion. The theorem is, we already guess, we can guess what we are going. Let xn that be an Markov chain, an irreducible Markov chain, positive recurrent state, positive recurrent Markov chain. Since it is irreducible, and if one state is positive recurrent, then every state is positive recurrent. If no state is positive recurrent, then it has no stationary distribution. So to have a stationary distribution, that the chain must be positive recurrent state. That means all the state must be positive recurrent because it is irreducible. Remember. So positive recurrent Markov chain having stationary distribution. So to have a stationary distribution, that Markov chain must be positively recurrent. Distribution say pi. If the chain is aperiodic, that chain is aperiodic, then this is a stationary, the steady state stationary distribution. So this goes to pi y for all xy. So whether it start from any x, that Pn x goes to y, Pn x to y, that positive, that probability of the n step probability, that n tends to infinity, that goes to that pi y, that stationary distribution. It's converse to a distribution. So this is it is for positive recurrence, irreducible chain. If it's not positive recurrent, then no stationary distribution exists. Now, if it is not irreducible, the idea is same. If it is a reducible Markov chain, then you just look at the all irreducible component and maybe some component which are not positive recurrent, maybe non-recurrent. So you just look on the the irreducible component which is not positive recurrent, that have no stationary distribution on that, concentrate on that. So you just look on that individual positive recurrent component, positive recurrent irreducible component, and each have a unique stationary distribution which is steady state distribution, and just you can just take a mixture of that to take the stationary distribution. Now, if you have a distribution, initial distribution is constant on some irreducible component, that positive recurrent irreducible component, that then goes, that distribution as n tends to infinity goes to that P and X, Y, that goes to that unique stationary distribution constant on that C1. And if you have some distribution, say start with this initial distribution with say is constant on C1 and C2 both, that is a mixture of, then that means we have that converts to a mixture distribution, converts to a stationary distribution, that is a mixture of that distribution, two stationary distribution concentrated on C1 and C2, the mixture of that. So this is the basic idea. So we already complete the discussion. So this is, and the last thing is, if the chain is not periodic, then what happens? If the chain is periodic, is periodic, then what happens? Is periodic with some period d, d is positive greater than 1, with some period d, obviously d greater than 1, strictly greater than 1, then for each, then what happens? It is then for each pair xy in belongs to script, then the state space, there is an integer r r is between 0 and d, it can be d, it's strictly less than d, such that Pn xy is 0 unless n equal to md plus r. So there is an integer r such that say d is say 5, the period is 5. So since it is irreducible, so every state has the same period, whether it is positive recurrent or not. So what is we are taking is a positive recurrent Markov chain, irreducible. So every state has a period d. Let's say 5. Now from x to y, it goes into the 3 steps, say, with positive probability. That means x to y, we can go to the 3 step, we can go to the 8th step, we can go to the 13th step, but we can't go to in the 12th step. That's an obvious thing. So it's a congruent class. All sort of congruence classes, z modulo 5, z mod 5, z congruent classes. It's just the remainder is the 3. Then that's all the elements of the remainder 3 that have this positive probability. And other than that, this is 0. It can't go to the from x to y we go to with the 3 step with positive probability and the period is 5. Then from x to y you can't go with 12 step or can't go with 4th step. That's the theorem. So and obviously for some integer such as this, unless for this, and for some non-negative integer, for that is true for some non-negative integers. So for some non-negative integers, that is a natural number or maybe 0, m may be 0, m may be 0. So it is r n equal to r maybe. And the last thing, in that case, is this something is converged to the pi y? No, that is not true. That something cannot go to the pi y. But what is true, that m tends to infinity, that pm, not any n, that is pn plus r, because other than it is 0 for the special r. From x to y, that probability is not just pi of y. This is actually because it is not coming to the 1 step, it is coming to the 2 steps. So that's why in the after d step, so d actually is accumulate all the probability, so it is d into this. So it is d into pi y. So it's not converts to the stationary distribution, because d into pi y is not the stationary distribution. So it is not if you take any other r. So if you take md plus r dash, which is r dash not equal to r, then it goes, this is 0. So that means if for 1 6 this is 0, 1 6 11 2 7, that is 0, but only for 5 10 that is not 0, say. That's why it's actually take all this probability, all 5 probability. It's actually for 5, it's take all this 1 2 3 4 5, it's club all this probability, so it's 5 into that probability. So this ends the Markov chain thing. Is in a good point. There is some other aspect of this thing, but we are not going to proof of that theorem. This is slightly longer proof. Intuitively it is clear, but it needs some longer calculation, so we are not going to the proof of this precise proof of this. And there's some other aspect of this Markov chain also, but we can stop this course here. Is in a good place whether we learn is a moderate thing about the Markov chain. So that's in this lecture and as well as the course also.